But I realized I made a big mistake in the title of my slide. I really should have said the wireless singularity at Salt Lake City, Utah. But I'm going with a more modest towards frictionless reproducibility in the Powder platform. I'm a professor in the School of Computing at the University of Utah, and I'm the director and the lead PI for this NSF-funded initiative called the Powder platform. So we are part of the Power initiative from NSF, and there are a couple of sister projects, if you will, associated with that initiative as well. So I'm first going to give a very brief overview of what we've been calling our ecosystem. So we have these three main components. I'm going to talk about the platform, bottom right, which is sort of the main thing, right? This is the thing that enables all the other things. But we've sort of grown over time, and we are now an ORAN Alliance OTEC, and I'm going to tell you a little bit about that. And we're also funded as part of the NSF National Radio Dynamic Zone program, which is part of the SII Spectrum Innovation Initiative. And we're prototyping a radio dynamic zone on Powder. So I will talk about all these things, and then I will move to a little bit of the how we are moving towards frictionless reproducibility in our environment. All right, so the platform, this is sort of my comic picture of the platform, the bottom left. So we basically look like a cellular infrastructure. So we have stuff on rooftops, we have stuff in dense, what we call dense nodes, so small cell kind of configurations. We have private front haul to a near edge compute facility. We have big compute infrastructure behind that. We have devices that kind of sit in the UE or the endpoint configuration that are fixed on buildings. We call them fixed endpoints. We have some of those on buses. And, you know, so in some sense, this just looks like a regular wireless infrastructure. The key thing for us is this is all open, it's remotely accessible, and critically, we are open source and we are open as low as we possibly can, right? And I'll say more about that later on, but critically our radios, most of our radios are software defined radios. We do have some off the shelf or common off the shelf Koch UEs and now ORAN radio units as well. So we have a little bit of a mix, but the way we think of what we have is a bunch of building blocks, software and hardware building blocks, that a user of our platform can come and put together into an end-to-end experiment. And for the duration of the experiment, that's theirs, right? So we set it up for them and then we get out of the way and they do their experiment. And once they're done, we kind of rinse and clean and it goes back into a pool, as it were, and become available for other users, right? So that's sort of maybe in some sense, the first level of reproducibility is that this is the model that we work with, time and space shared. We have a sophisticated experimental control framework, which I will talk quite a bit more in the second part of the presentation. We're in FCC Innovation Zone. Happy to talk more about that. And again, as you will see as I go on, we try to enable bring your own device, bring your own software kind of capabilities, right? So if you're like, well, I'm a company, I'm not interested in your SDRs, thank you very much. We would still like to accommodate you, right? And I have some examples to show that. So sort of the takeaway here is the way you should think of this is it's a highly flexible, interesting. I'm sure I spelled that correctly. Maybe this was in the translation to PDF. This is a very flexible, real-world lab as a service environment, right? So the thing that we provide is a lab as a service, but in a real-world environment. Okay, here's some pictures just to give you a sense of what this looks like. The On the left, we have the rooftop nodes, right? This is a temperature-controlled environment on rooftops. We have that on 9 rooftops on our campus mostly. The green ones are the dense nodes, so smart lamppost kind of thing, cabinet at the bottom, a pole, antenna at the top. The orange ones there, that's what our fixed endpoints look like. So more or less human height, although the specific example here would have been a tall human. And then the map there in the top right shows sort of geographically what this looks like. So the red area there is University of Utah campus. On the left, you can sort of see the yellow coming out there, the Salt Lake City downtown area. So right in the bottom left corner, the University of Utah Downtown Data Center, that's where we have a really big compute cluster. It's actually part of a different NSF initiative, but we're connected to that. And then on campus, we have all these different components. We have a near-edge compute facility. We have another compute cluster in our own building. So lots of components, hardware-wise, that we can flexibly stitch together. As I said, we have devices on buses, right? So these are campus buses. We have a little box in the back of about 20 buses, has an SDR in it, has COTS UEs in it. And again, these things are for us components that as a user, you can get access to, and it can become part of your experiment. And then on the left, the blue, we recently started deploying ORAN Alliance COTS radio units. I'll say a little bit more about that, but so that a little bit less flexible, of course, because now your radio unit is standardized, but it has its benefits, right? So these COTS are commercial equipment, and there are now open source stacks for the DU and the CU, and so we kind of give you a slightly different point in terms of the flexibility and what you can do with that. Okay, here's a very quick illustrative example. And again, I'll go a little bit more into the how we do this later on, but just to give you a flavor, right? So we can stand up an end-to-end 5G network in less than 10 minutes using this facility, right? So you would come in, you'd select the appropriate profile, and I'll say much more about profiles later on. And 10 minutes later, this thing is operational. And it's operational with endpoints, right? The buses on the right-hand side shows the different colored blobs, shows the buses that are part of this experiment with COTS UEs associated with them, and the top right shows the Grafana interface. So at this point, we're collecting end-to-end data associated with this experiment. And this is open source based, so you can modify it and you can add to it, you can do your research with that. Okay, so moving to the second part, as I said, we are an ORAN Alliance OTIC. For those of you who are not familiar, OTIC's Open Test and Integration Center, and they're cheaper by the dozen kind of thing. They're popping up all over the show these days. Our specific focus, given where we're coming from and the capabilities that we have, is end-to-end and functional testing. And so we realized early on that this automation that we have in the framework, right, the way that we can put together these components into an end-to-end setup is pretty unique, but it only supports part of the story, right? If you then want to do testing of your end-to-end ORAN or 5G or NextG setup, really that's another layer of automation. And so we developed this thing that we call TODA, testing orchestration and testing automation. And again, I'll have a more concrete example later on, so I'll just briefly go over this at this point. Basically, there's it's largely open source components that we use, but this framework that has a workflow associated with the testing that you want to do. And on the left, it interfaces with the platform, and that's the orchestration part, right? So all of this stuff that I talked about earlier, you can now think of as saying, oh, yeah, that's how I put it end to end. I want this piece, that piece, I want it set up like so. And then once it's set up, the rest of this kicks in, and we can now do automated testing. Right, so this might mean configuring some devices, running a test, siphoning off the results into a test case management system, rinse and repeat, right? And so again, this is another level of repeatability, but a little bit more at the test and automation level. So some illustrative examples. We're working with a private 5G vendor, Salona, and you know, we started testing with them in our lab environment, and then we moved them outside into our over-the-air environment. And so they co-located in some of our what we call our dense nodes. So the picture there at the top right. Excuse me, and we have an RF switch so we can pick which radios we use. And they are now at this point where they have a new release of their software. You know, their engineers in some other place of the world, I don't know where they are, come in and they swap in their experiment. And I'm bleeding here a little bit into the terminology that we use. And they do regression testing, specifically interested in doing handover in a real world environment. And when they're done, they release all the resources and someone else can use it. It's a nice example. On the bottom right, we're also testing with Mavenir, ORAN vendor, US-based ORAN vendor. So they recently deployed the millimeter wave massive MIMO equipment on one of our rooftops, and we've been deploying CPEs for them as well. So in this case, our testing is really more around the testing on top of what they provided, right? But again, they kind of make use. This is a mix of their equipment, our equipment, put together in an end-to-end setting. And then the final example here, we just in the most recent ORAN Alliance Plug Fest, worked with SRS RAN. So they're sort of a mix. They provide open source software, but they're also a commercial entity, as you might know, with them and some off-the-shelf RUs to test their handover capabilities. And that specific one we did in a lab environment, right? But this is the kind of examples that we do. All right, third component is the powder RDZ. So as I alluded to at the beginning, this is a separate part of funding, part of the NSF Spectrum Innovation Initiative. And we were specifically tasked to prototype a radiodynamic zone. All right, so what is a radiodynamic zone? It's the easiest way to think of that is the flip of a radio quiet zone. So if you want to do RF transmissions, this is a zone, a place, a 3D place, typically, where you can come and do that testing. And there would be the machinery, the mechanisms, the policies, the tools in place that allow you to do that testing without causing harm. All right, so quote unquote, causing harm, right? So what that means is, as we've seen throughout this week, depends on the use case and on. But that's sort of in a nutshell what an RDZ is. So given the platform that we have, we've been tasked to prototype the workflows, the architecture of such a thing. And so on the right there is the architecture that we came up with. And one of the key things that we did all the way through is to say, yeah, we're doing this on powder, but we don't want it to be powder specific. We want this architecture to translate to other locations. So we came up with this abstraction layer, a zone abstraction layer, ZEAL, and we came up with clean APIs for those, and basically these three role players, right? So at the top, the yellow, is where is your spectrum coming from for this test that you're gonna do, right? This, whether that's through an SDA or whether you have a program experimental license, on and on. In order to do this, you need some notion of what spectrum you can use. And then at the bottom, the purple is we probably should monitor what's going on spectrum-wise in this environment. And then the piece in the middle, the, peach color, that's sort of the spectrum consumer. Right? So this is the thing that's going to do spectrum testing in the zone. So in our case, there's, of course, the powder platform, but this could be anything else. And it doesn't have to be automatically or programmatically associated with the setup, right? This could be, someone brings the radio and you talk to a person and you say, all right, configure your radio for so-and-so, and all of that, you still make use of the flow through the system. Right, and then critically, the thing on the left, the purple and pink is the zone management system. And we call ours Open ZMS because we've actually open sourced this. And in a nutshell, you can think of that's the spectral intelligence. That is the thing that is going to know about the spectrum use, the spectrum entities, the transmitters, the test transmitters, everything spectrum related is delegated to this entity. And it is in the loop to control all spectrum use in the zone. All right. So with that big picture, I'm going to walk through some illustrative example. I'm going to walk through our program experimental license example in excruciating detail in a minute. But just to give you the context, right? We're a test bed, a wireless test bed. We need access to spectrum. The way that we typically get access to spectrum is in two ways. We have a program experimental license. We're also an FCC innovation zone. What that basically means is we have permission to use spectrum in certain ranges so long as no one else is using it. Or, so long as we don't interfere with anyone else. So we can use it. Doesn't necessarily mean it's useful or usable, right? And so this is sort of the piece I'm going to talk about more is just automating the spectrum use in our environment. As part of our work, we are also exploring other use cases, and I'm happy to talk about these offline. Mention these two, right? So we have a collaborator from AT&T involved, and the picture at the top right is showing what is fairly common these days with commercial cellular providers. They have a lot of need for spectrum, but not all the time. To save energy at the middle of the night or at other times, actually, they might put their cells to sleep or idle them. So these are measurements that we took in our environment. And the essence here is just showing that at certain times, there's an effective space in the spectrum that is unused. Now, is that useful generally for commercial use? That's unclear. Is it useful for a test bed? Absolutely. Right? If we can get access to the spectrum in the middle of the night and schedule our users' experiments to make use of that, we'd be golden. Right? So this is a use case we're exploring. Another one that is clearly more controversial, I've found, is sharing with federal radar systems. So I'll very briefly say there, so we're specifically looking 2.7, 2.9. These are the weather radar systems and the ASR 9, the airport radar systems. They effectively use fairly little of their spectrum, right? So it's 200 megahertz in our environment. There are two of these systems close by. We've been working with Nick Lasorte at NTIA, and we're pretty sure that there's a big chunk of that spectrum that we would be able to use safely. Now, we're not using it. We're in the, let's analyze this and see if we can convince the agencies involved for us to do a very carefully controlled experiment. But these are sort of two other things that we're doing with our study. All right, let me transition to the program experimental license workflow. So again, the goal here is to say, well, we have permission, as it were, to use certain spectrum ranges, but can we actually use it? So here's how it would go through an OpenZMS, right? So you would start up, you would initialize the OpenZMS. Who are the role players? What is your geography? What is your RF propagation models? And critically then, what spectrum are you allowed to use according to your program experimental license? So then, we have a monitoring system deployed, and so a key thing for the OpenZMS is to see what's going on spectrum-wise, right? And so intuitively here is like, well, yeah, we have all these spectrum ranges that you could use, but what is actually in use? Can we fit you in terms of these other users? So the way this would go then is the spectrum user, so in our case, this would be an experiment running in the Powder platform, would make a request to the OpenZMS and say, hey, I want to do an experiment. I need this much in this range. the OpenZMS would consult with a digital spectrum twin, right? So this is the actual smart thing inside of the OpenZMS that make these decisions. Again, I'll say a little bit more about that momentarily. So this is saying, okay, given what I know, based on models, based on measurements, can I fit you in? And let's suppose the answer is yes, I can fit you in. Well, can I fit you in? And given what you told me about the power levels you'll be transmitting at, can you safely operate in the zone, or are you going to spill out, right? And let's suppose, I think I said that one already, and let's suppose the answer is yes, then it goes back to the user and say, go ahead, use it. Now, in our environment, we actually have inline monitoring of our, especially our SDR equipment, right? SDR equipment, as you know, can operate anywhere. It could be just an honest mistake, but we want to know when our users do something bad. So let's suppose someone is operating in on a spectrum outside of what was allowed. We would learn about that because we continue to monitor, and we tell them to terminate, or we would terminate the experiment for them. All right, so this is basically the workflow. This is just pretty pictures showing that. Top right hand, that's what the OpenZMS portal looks like. Bottom right, this is an actual graph of utilization in our area. We have C-band operators, actually lots of CBRS users, and then the little blip at the bottom left is our test transmitter, and the left-hand RF propagation here is showing the zone, and are we okay in terms of transmission not going outside of the zone at certain power levels. I need to say a little bit more about the digital spectrum twin. This is an idea that was coined, as far as I know, by Greg Durgan from Georgia Tech, and we're very glad to have them as part of our team. And so we have essentially two RF propagation models. One is this TIREM-based one that comes from Greg and his team. We're also making use of a commercial system from Altair called FICO. And this is basically, and this is the space many of you are working in, so I'm not going to try to explain this to you, but, sort of layers of maps as you go up and as you add to that. But the essence here is starting with a TIREM model and then trying to improve the accuracy through measurements. And they've also done some work in terms of applying machine learning to that to increase the accuracy, which, again, I'm not going to talk about today. Okay. Like I said, we made this open source. There's sort of an architectural picture at the top right. And the goal here is, from our perspective, is to create a solid framework that's open and flexible that others can use and plug into, right? So we're actively trying to make this into a community open source effort. And we've had some early success. So we worked with Kevin Gifford at the CU Builder, and he introduced us to the folks at Hat Creek Radio Observatory, and we did a small trial with them where we took OpenZMS into a different environment and did some testing with them. Right, that's the first part of my talk. I'm now going to switch to, how am I doing time? 10 minutes. I can do that. Okay. Oh, questions. All right. So a little bit more detail below that. Missed that? Okay. So again, we think of what we have as building blocks, right? And so a key concept for us to make all of this work is what we call profiles. Right? And a profile, you can think of it as it's a recipe. The recipe says what you want, how you want it configured, the software associated with that. And just going through the flow here, user would come into the portal. Typically, they would pick a profile, or they might create their own. That gets handed off, or that gets parameterized. That gets handed off to a control framework, and that instantiates the experiment for them. And again, then we kind of get out of the way and allow the users access to that. Okay, a little bit more on profiles. Literally every resource in our environment is specified in a profile, including spectrum, radio, of course, the servers and the network and their configuration. Right? That's the easier part here. It is parameterizable. is version controlled. You can also have it as a Git-backed repo, so even the recipes can be version controlled. So like I said, we provide a library or a database of ready-to-run profiles, so things that will work in this environment. But the recipes are things users can create as well. Now, they can create it from scratch. More typically, they take one that's kind of close to what they do that we have provided, and they modify it, make it their own, and there you go. So everything I talked about so far, literally everything that happens in this platform is profile-based. So it's really the key reproducibility mechanism for us. I'm just going to run you real quick through the screenshots here. So this is, if you have selected the profile, this one happens to be an open air interface 5G profile operating over the air with Open5GS as the 5G core. You select that profile, you go to the parameterized page, right? And you say, oh, I want these locations for my radios. There's a finalized page where you can look to see whether those resources are available. And, we're not going to go into that, but we also have a reservation system where you can say, oh, it's not available right now, but can you reserve this for me at the first possible time? And then there's a finalized page, and you can say how long your experiment is going to last. Of course, you can extend it later on if no one else needs it. And then you instantiate it, right? And on the left hand here, this is what you would get. This would be the experimental view. Those green nodes are now fully operational, right? There's the G-Node Bs, open air interface in this case, but could be anything else. And there's the core, and there's an orchestrator node that you can sort of use to interact with it. On the right is a similar profile, and I'm not going to go through it again because the flow is exactly the same, but for our mobile endpoints, right? These are the endpoints on buses. So once you have these two things set up, you're golden, right? So now you have an end-to-end experiment, COTS UEs with a 5G setup. And just to belabor the point here, we can, on the right-hand side, use the same endpoint profile for the buses, but now let's swap out the open source stuff and swap in profiles that we created for our private 5G vendors, right? So it's a different core, it's their core, it's a different RAN, it's their RAN, but now they have an end-to-end system. And again, we have space and time sharing, so this all works out. Here's an example of one of our users that have created their own profile and published it with their work. So Mobicom is a high-quality research venue. So these folks, this is Mahesh Marina and his students from Edinburgh University. They got a paper accepted to Mobicom. They published their profile of their experiment as part of their paper and made it available to the community, right? So nice example of actually that reproducibility. So you can go in and literally have a link, click on that link and walk through that steps that I showed you and instantiate their experiment. We have other users too that have done this. So the ORAN software community folks have been using profiles for their testing. Right, so if people are familiar with sort of automating things, this is a beautiful environment for them, right? So we didn't even know these guys were using it. And then we look at the usage stats, they were right at the top. And I'm like, what are you guys doing? And so, they've automated their testing of this open source software. On the right-hand side are the Selenium research folks. They were part of the DoD Spectrum Sharing Challenge. They've actually, I mean, this was a while ago, but they've made Powder part of their automated workflow. That's what the picture there at the bottom shows. 5 minutes. Okay. A little bit more detail on that TOTA, testing, orchestration, testing, automation. And I already gave you a flavor of that, right? So the number one there is just this workflow engine. And we have two versions of that, Stackstorm and Daxter. Daxter is a little bit more programmatic, right? If you want to program it. Stackstorm is if you're not interested in programming. And so we're kind of experimenting with both. But so you'd have a workflow that says, oh, here's the test I want to run. That workflow engine will interface with the Powder platform and set up your experiment. basically select one of these profiles and set it up. And then 2, 3, and 4 is like, oh, okay, now I have my experiment set up. Now I go through that, I change, I modify the configuration, I run my test, I siphon off the results, and there we go. A little bit on repeatability in terms of mobility. Right? So that's a little tricky. So we have sort of two ways we think about it. One is we have I don't think I mentioned this earlier, a programmable conducted RF attenuator matrix. This is great. Right? You program this thing, you pretend that you're further away. It's not very sophisticated. It's not a channel model or anything like that. But if you want to do handover testing, this is great. Of course, we have the buses going around, and you know how buses are. They're on the same route, right? And so you get a little bit of repeatability out of that. So that's sort of what we have in terms of mobility, repeatability. What about spectrum and RF conditions? And, you know, I don't know, maybe the argument is the point of an RF or a wireless testbed is that you want to repeat the same experiment in different RF conditions. So that'd be my cop-out answer. But in reality, I think we really want to know more about what's going on off that spectrum environment. Right? Can we get to the point where we can capture the spectral conditions, or that we can say, oh, you know, the difference between when you ran this experiment yesterday or maybe 2 years ago and now is thus in terms of the wireless conditions. So the pictures here, sorry, I forgot to say this. This is just CBRS, and it's showing how it changed from 2021 to 22, 23. And, you know, it's just, this is a dynamic environment. Things change. People bring up new base stations, G-node Bs. And so, yeah, I think this is a big challenge. I don't know, maybe our OpenZMS might be an initial approach to that. All right, I'm on my last slide, maybe. So what makes wireless frictionless repeatability hard? So first of all, the wireless environment is changing, and I don't have to tell you guys that. I would say this kind of real world lab setup is hard to manage, right? So we are trying to do lab kind of stuff in a real world environment, and it's hard. It's a complex ecosystem, right? So one of the things, I mean, we speak to faculty all the time, and they're like, oh, I have this research idea. I want to use your testbed. And just doing that mapping, even with someone that knows what they're doing, is hard. And then, yeah, the testbed is just hard to use, right? So we have all these tools to try to make it easier, but it's still hard to use. The domain science is rapidly evolving, right? So we barely have these open source 5G stacks working. And people are like, 6G, right? Well, why are you still messing with 5G? Well, this is more of a continuum than it might seem. But then there's the open source is great, right? And so open source, not all open source is equally endowed, so to speak. I mean, there are some of these open source stacks that are production quality, and some of them are way more experimental. And you kind of want to have them all because they have different trade-offs. It's inherently cross-disciplinary, right? And this maybe gets into the workforce training thing. I mean, this is what we've seen. So we have people from the EE side and people from the CS side on our team, and we really need both sides, right? And so we've been thinking of training in that direction. And then finally, stakeholders have different interests and different needs and different skill levels. So we started out more as a academic testbed, but we've been chartered from the get-go to also support non-academic research. It's like the things that they want are really not the same. And so that, presents a major challenge. All right, that's it. Thank you.
Okay, any questions? Maybe squeeze one or two rapid fire questions.
Real simple technical question. What frequency ranges are you covering typically? What kind of power levels? And then also what kind of survey accuracy do you have for your fixed antennas? Obviously the mobile ones are coarser.
So it's a simple question with a not simple answer. So as I said, we're FCC Innovation Zone, so we're allowed to use different ranges. We have SDRs that do not have RF front ends. So if they can transmit, and again, well, what is the antenna that you have connected to them? And we have different antennas, different places. Some of them broadband, some of them are cellular CBRS 5 gigahertz. And then we have different, the dense nodes, the picture that I showed with the actual end-to-end 5G, we have an RF front end at the front of the SDR. And those are sort of C-band and CBRS, right? So what would that be? 3.4 to 3.8 or thereabouts. So that's the answer, right? It depends. And then the COTS are used, they're N78, so roughly the same band. Oh, there was a second part, the accuracy, not very accurate at this point, right? I think we do this, we have essentially a profile that gets kicked in when no one else is using it, and we do scans of the whole spectrum range, so up to 6 gig. And we have those just basic occupancy measurements. They're not super detailed. They're very helpful still. I can't tell you how often we go back and like, okay, what did anything change, right? And so that's sort of a little bit where we need better spectral intelligence comes from, because I really don't want to troll through 100 pictures and try to find this. I want to hit the button and say, what changed from this date to that date? Was there a change? So yeah, that's the answer.
Yes, very good work. I'm trying to understand, you called it a recipe. I thought that was cool. How do I compare the recipe of access that you were able to optimize to benchmarks like, listen before talk in the unlicensed or deterministic protocols?
Yeah.
State of the art.
Good question. So the way I think of the recipes, and that came out maybe more in the the TODA thing I talked about at the end. The recipe part, think of this as you're going to do an experiment in a lab. Well, what's the first thing you're going to do? Is you're going to say, oh, what's the equipment? How do I position them? How do I configure them? What software do I run? Now I start my experiment. That first part, that's the recipe part. It's just setting the thing up for you, okay? The second part comes in to say, okay, well, once I've set it up, what do I do with that, right? And sometimes, like in some of the more sophisticated users examples that I showed, they, now it's set up, they do their own thing, they do their data collection, they run whatever they run, right? But what we've done more in the OTIC context is to say, well, maybe in this context, you want to run the ORAN Alliance end-to-end TIFG blessed set of tests. Well, maybe that's what we'll use, right? And so that would be sort of the standard test setup that you then step through. So that's sort of the way I think of it. Okay.